Okay, so here's a brief summary of the two sections we covered from Chapter 9 on differential equations. Differential equations. All right, so just to start, what's a differential equation? Remember, a differential equation is one that relates a function and its derivative or derivatives. So it could involve, first derivative, second derivative, and so on, potentially. Here's just a quick example of that. Let's say y plus y prime plus 2y double prime is equal to 4. Okay, so there's some equation involving the function y and some of its derivatives. All right, solutions to equations. So a general solution to a differential equation is essentially an expression that has some unknown constant in it. Okay, so this is like our plus c, our constant of integration. So it's similar to that. We'll have an unknown constant. Okay, so this is the general solution. So for example, a solution like y equals c times e to the negative x over 3. Okay, there's a general solution to some differential equation. We can find a particular solution if we have an initial condition. So that means we can solve for that unknown constant. So when we say particular solution, that would mean that I would want to know what capital C is in that example that I just gave. So we can find a particular solution if we have what's known as an initial condition. And often it's written as something like y of a, say, equals b, something along those lines. So for example, let's say that we have the general solution y equals x over 2 plus c, and then the initial condition, which is y of 10, let's say, is equal to 2. So this is giving us some specific value of the function at a specific x value here. What we would do with this information is, so remember, like this is the y value here, right? Y equals, this is the x value that we're plugging in. What we would do is say, okay, well, in my equation for the general solution, replace that y with the 2, replace the x with a 10, and now we can solve for that constant c and find that particular solution. All right, so now on to separable equations. Okay, so separable equations, what are these? These are equations that can be arranged to have this form. Dy by dx, or y prime if you want, is equal to some function of x times some function of y. So you have to be able to solve for the derivative. So this could be y prime. So y prime or dy by dx there. But you have to be able to solve for the derivative and then factor whatever you have so that all the x's appear in one factor and all the y's appear in the other. So here's an example of this. So dy by dx equals cosine x minus y times cosine x is separable. Okay, why is it separable? Because we can rewrite it as dy by dx equals cosine of x times 1 minus y. Okay, and then what's a non-separable equation? Well, So that was a separable example, and then say dy by dx equals 2x squared plus y, say, is not separable, right? Try to factor here. See what happens. I can maybe factor out a y and say, okay, well, factor out y, equals y, and then that leaves us with a 2x squared over y. Like, I can't get it out of that term. It does leave us with a plus 1 on the end, but that doesn't really help, so there's still a y in there. Right, so I factored out this y, but then the other part isn't all x's. It has a y sitting in it, so that makes this equation not separable. Okay, and then once we have a separable equation, right? Right, once we have dy by dx equals f of x g of y, right, we can solve by separating our variables. Okay, so what does that mean? We're going to collect all the y's on one side, meaning we'll get 1 over g of y dy equals f of x dx, and integrating on both sides. Okay, so what's an example of that? I'm just going to take the separable equation we wrote down above. So dy by dx equals cosine x times 1 minus y is going to become 1 over 1 minus y dy is equal to cosine x dx, and we just take the integral on both sides. Okay, so there's obviously solving to do from there. A constant of integration comes into play, and that's where that unknown constant in our solution is going to come from. But that's our setup for solving a separable equation, is writing it in that way, and then integrating. So let's talk about some specific separable equations that we encountered in 9.3 now. So mixing equations, right? So there's some substance that's suspended in a liquid in a container. So the setup is the following. We're going to let y equal the amount of the substance in the container, so inside the container, at time t. Okay, anytime t. So the differential equation for y is dy by dt equals the rate at which the substance is entering minus the rate at which it's going out. Okay, so let's break down these pieces. The rate at which we're going in is going to be equal to the concentration of the solution going in times the rate of the volume going in. Right, so sort of how much liquid is going in. Whereas the rate out, that's going to equal the concentration of the solution going out, again, times the rate of the volume going out. Okay, furthermore, this part, the concentration of the solution going out, is going to equal the total amount in the container divided by the total volume in the container. But remember, the total amount in the container is y. So this part is going to be y over the total volume in the container. All right, and that's sort of our general setup for solving these mixing equations, which are separable. The other specific type of separable equation we encountered was orthogonal trajectories. Okay, so we give a family of curves, and then we want to find another family of curves that are all perpendicular to the one we started with. So the general way this goes is that we'll take our original equation and find dy by dx. We might need implicit differentiation. So I'll just make a note on that. So might need implicit differentiation. This is a family of curves, so there's usually sort of some constant k involved in the equation, and step 2 is just to eliminate that from dy by dx. So eliminate k from that derivative. Okay, so we just have dy by dx is some expression often involving y's and x's. Now we write down a new equation. Okay, and the new equation is dy by dx is the negative reciprocal of the derivative we already found. So it's minus 1 over the derivative that came from steps 1 and 2. Okay, so we found a derivative in steps 1 and 2. Step 3 is to write down a new equation where dy by dx is minus 1 over that derivative that we found. And then this is a separable equation. So now in our new equation, we separate our variables and solve from there. Okay, so and then orthogonal trajectories, very much related to sort of electricity and magnetism. That's where you might want to find curves that are orthogonal to one another. What's the other thing I should say? With the mixing equations, the rate of volume going in and out, those do have to be the same to make the equation separable. So that's often what you'll see, like on WebAssign, the amount of liquid going in and out, or the rate of liquid going in and out, is equal for that reason. All right, so that's our little summary of differential equations here.